Hi everyone, Rebecca here. In this video we are going to be talking about insertion sort in excruciating detail. If you want to know how or why insertion sort works, this is the video for you. Alright, the way that we're going to do this is we're going to start by discussing a possible chant that you could use to implement selection sort, the algorithm. Then we're going to step through an example of applying insertion sort to a list. We're then going to discuss the algorithm for insertion sort at a higher level. We're going to code it in Python, and then we're going to put it all together. If you want to jump to a particular section in this video, there will be timestamps for each section in the description below. Let's get going. So the chart that I use for insertion sort is a little bit, it's less pithy than the selection sort chant. If you come up with a better chant than this one, please put it in the comments. I've been looking for a better chant for the past couple of years. So the chant that I use is look left and lumber. So lumbering just means walking in a fashion. The only thing that this particular chant has going for it is alliteration. Now, just a reminder, and I discussed this in the selection sort video as well, the reason I like using chants when I implement algorithms is for two reasons. The first one is that it can be really nerve-wracking to implement an algorithm in stressful situations like tests or interviews. So it can be helpful to have a chant to act as a mnemonic device, so that's a memory device, under those kinds of stressful situations. The second reason is because when we are implementing an algorithm as human beings, we are essentially role-playing being computers. And computers are incredibly good at doing boring, repetitive tasks over and over again. Humans, we're not so good at that. So the chant acts as a tiny little bit of entertainment value in order to keep us engaged so that we don't just drift off, so that we are actually capable of semi-pretending to be a computer. Of course, if you decide not to use this chant, that is absolutely up to you, and I will not be offended at all, particularly given I won't actually know. So feel free to completely ignore this aspect of this video if you so desire. Alright, let's see the chant in action. So here we can see the same list that we had in the selection sort video, and we are going to sort this list by using look left and lumber. As with selection sort, we have to start this off by setting some k, so some element to start looking at. Now with selection sort, we started with k being the first element. This doesn't actually make sense with insertion sort. The reason being that we are looking left, and it doesn't make sense to look left from the start of a list. There is nothing to the left. So with insertion sort, when we set up our k, we set it up at the second or the 1th element. There we go. Alright, so now we're going to look left. And you can see that our list has now gone green in the direction of where we're going to be looking. And we lumber. Now, in order to keep track of the various states of our list as we apply insertion sort, we've actually created a new line, and that's where we're going to do the lumbering. So all the lumbering means is the number that is red is going to look to its left, and if the number to the left is bigger, then we're going to charge into it. But in this case, the number to the left isn't bigger, so there's nothing really for us to do here. So we're just going to move our k up by 1 and continue with the algorithm. Alright, now once again we're going to look left, and we're going to lumber. So we've got our red number, and our red number is looking left to see if the number to the left is bigger, and in this case it is. So we're going to swap them. Once again, we're going to look to the left and see if the number to the left is bigger. Well, it isn't. So we're going to move our k up by 1. All right, we're going to look left, and we're going to lumber. So tell me, should there be a swap occurring? Well, yes, there is, because the number to the left was bigger. Should another swap occur? Well, yes, it should. And another swap. All right, we've now hit the point where there is nothing to the left. So we can't continue lumbering. We have to increment our k. And there we go. All right, once again, let's look left and let's lumber. But there's nothing to lumber into. This number is smaller, so we're just going to increment our k. And we're going to look left, and we're going to lumber. Is the number to the left bigger? Yes, it is. So let's lumber down. Is this number bigger? No, it isn't, so we have finished lumbering. We're going to increment our k, and now our k is off the screen, off the board, off the list. It's out. We can't fit it anymore. So that means that our list is sorted. Now, there are a couple of things I would like to draw your attention to. The first one is, we wrote down intermediate states even when there was no change. It is really important that you do this when you are in an exam or an interview situation, because often what your interviewer or your examiner is testing is that you understand how the algorithm works. And under the insertion sort algorithm, you're going to get times when there just isn't a change. Secondly, there are as many states as there are elements in our list. So this is exactly the same as selection sort. If you remember, selection sort, when we did it in the selection sort video with exactly the same list, had 6 states. So one of the states was the unsorted list, one of the states was the sorted list, and then we had these intermediate states. Similarly with insertion sort, you will always have as many states as there are elements in your list. While we are on the topic of selection sort, I would like you to compare these intermediate states with what the intermediate states were in selection sort. And you'll find that they are very, very different. Even though selection sort and insertion sort both give you the same outcome, at least in this particular case, the way that they get there is totally, totally different. And it's really important that you understand how they are different. Now, finally, you can see that I have tracked my k as I went down. This is a really good thing to do when you're doing this in a test or an interview situation, because otherwise it can be really, really easy to lose track of where you're up to. So if you just track your k, so you might do that by simply underlining it if you're, writing this down, you'll find it's easier to go, all right, so this was my k, so that means that in my next line, my third element will be my k, and everything before that element will be in sorted order. And then in this line, my fourth element is my k, and everything before this element is in sorted order. If you don't track your k, it can be really, really easy to get lost while you're trying to implement this algorithm. All right, that's everything I have to talk about with this example. Let's now try coming up with some basic steps that give us the outline of our algorithm. All right, so as with selection sort, the very first thing that we did when we applied insertion sort was we set our k. The difference between insertion sort and selection sort was that in selection sort, our k was at the very start of the list, whereas in insertion sort, it was the second element in the list. And that was all because of the look left aspect of this algorithm. All right, the second thing that we did, if you remember, is we looked to our left, sure, but we needed to find some number that we compared to what was on our left. And we didn't actually use k to do those comparisons. Instead, if you remember, we actually made our number go red, symbolizing, a different kind of variable. Now, in the algorithm, we're going to call this j. So we set up j as equal to k. And just to jog your memory, I might even jump back into the example. So we set up our k, we looked left, and then we set up a j, and it was our j that did the lumbering. So the reason it's important that you have the j variable is because otherwise, once you finish with the lumbering, if you do lumber your j down, you need to remember where your k was at so that you can increment it by 1. So that's why we have two variables going here, j and k. All right, so we set up our k, we set up our j as equal to our k. Then if the item left of j is bigger than the item at j, we swapped the items and we moved j down by 1. So this was the look to the left and lumber aspect. And then, of course, we repeated this until no more swaps occurred. So it wasn't enough to have just one look to the left and lumber. We had to keep lumbering until it wasn't possible to lumber anymore. Then we moved k up by 1. So once we had lumbered as far as we could, so once that red number had gone as far left as it possibly could go, our k moved up by 1. Then finally, we just kept doing this until k was outside of the list. Now this was different to how selection sort worked, because in selection sort we were actually able to finish the algorithm when k was the last element in the list. So if you think about it, selection sort and insertion sort do just as many internal loops. That's a bad way to think about it. The repeat steps 2 to 5. Yes, the repeat steps 2 to 5, or in selection sort I think it was steps 2 to 4. That aspect happens exactly the same number of times, because in selection sort we started at the first element, but we stopped at the last element. Whereas with insertion sort, we started with the second element, but we stopped once we were outside of the list. So if you're not quite sure what I'm talking about, I recommend going back through the examples for selection sort and insertion sort and comparing how they are different, how they start at a slightly different place and finish at a slightly different place. All right, so they're all the steps in this algorithm. Then we want to think about how we could write this in Python. Now, a really good way of tackling complex algorithms and their translations into Python, or indeed into any coding language, is instead of thinking, I must translate the entire thing at once and it must be perfect from the get-go, you break it down into smaller steps, you translate those smaller steps, and then once all those smaller steps are done, you can then consolidate them into an algorithm and then clean up that algorithm. So that's what we're going to do here. We're going to go through each of these 6 steps and think about how we could implement these steps individually, and then in putting it all together, we're going to put them all together and think how we can consolidate these steps. So let's do that. Now our first step is simply setting up k. This is kind of so easy that I think you're probably bored. If you remember, in insertion sort, our k doesn't start from the first element, it starts from the second element, which means that we have to set our k to 1, because our k is pointing at our index, and the second element in Python is the 1th index. Our second step is setting up j is equal to k. Oh my goodness, this is so simple. And I like that it's simple. You can see how we've taken a complex algorithm, and when we break it up into its components, the components are really easy. That's really good. So setting up j is equal to k is just j is equal to k. Now we have step 3. If the item left of j is bigger than the item at j, swap the items and move j down by 1. So this here is essentially our look left and lumber. Now, this looks a lot scarier than it is. If we were to break this down, we would see that we've actually got 3 sub-steps. We have a check to see whether the item left of j is bigger than the item at j. If that check passes, then we do a swap, and we decrease j. So I think that the hardest part of this step is actually this check. If the item left of j is bigger than the item at j. So all this is saying is, inside my list, look at the item at j, and then look at the item left of it. Remember that j represents an index. So what is the index of the item that is directly left of j? Well, that will be the index that is smaller by 1. So it will be the index j take 1. And that's how we do it. So if the item in the list at j take 1 is bigger than the item in the list at j. And there's our check. So that is our looking left. We are able to look left by looking at the item at the index that is smaller by 1. Then if this is the case, we swap them. And remember, in Python, we can swap things all in one line. It's really lovely. We can simply say the thing at A is now equal to the thing at B, and the thing at B is now equal to the thing at A. So I really like the way that Python lets you swap things. And then finally, we want to move j down by 1. So that simply means we decrease j by 1. So there we go. It looks much, much scarier than it actually is when you break those steps down into descriptive words. All right, let's look at step 4. So step 4 is simply repeat step 3 until there are no swaps. So let's get step 3 up on the screen just so that we can remember what we're dealing with. Now, there are lots of different ways that you could implement this step. Given that we're being told to repeat this step until there are no swaps, one way we could do this is by making this occur inside an infinite while loop. And we would set a flag, swaps, to be equal to true, and then as soon as this if statement fails, that flag would be equal to false. Let's have a look. All right, so we've got swap is equal to true. While swapping is happening, do this statement, and then do this code block, and then if this if statement ever fails, set your swap to be equal to false. So that would be one way to do this. And you can see how this is a pretty direct translation of this instruction. But this probably isn't the best way to do this. So already, hopefully, you can see that this is a little bit more wordy than it needs to be. If you're familiar with while statements or with while loops, you probably know that there's a better way to break out of a while loop than setting a flag. We could simply use a break statement. So we could make this into an infinite while loop, so a proper infinite while loop, because we've got while true, so it's not a variable this time. We are hard coding in true. And then as soon as this if statement fails, we've got else break. So this will go forever and ever and ever until our if statement fails, and then we break. So this would be another way to handle this. Now, there is one problem with these two implementations that I've just shown you. So if we look back here, and then we look here again, they're pretty much of a muchness, but there is one case that they are failing to take into account. If you think back to our example when we sorted our list, there was one line in our list where we didn't stop because the thing to the left was smaller or the same. Rather, we stopped because there was nothing to the left. This particular implementation doesn't take that into account. So how could we rewrite this so that it does stop either when there's no swap because the thing to the left is no longer bigger, or because there is nothing to the left? Well, one way we could do this is by using a for loop. So instead of doing a while loop, where we loop and loop and loop forever until a condition fails, we could say to ourselves, well, I know that I could never loop more than a particular number of times. Namely, I could never loop more than the number of elements from the start of my list up until my k. So we create for j in range k, so that means we start off by setting our j to k, and then we go down by 1 every time we loop until we hit 0. So this will mean that we only do this check until our j is equal to 0, and then we stop. So this would be one way to implement this repeat step 3 until there are no swaps. And it's actually not a bad way of doing it. My only issue with this is that it's a little bit more verbose, so a little bit more wordy than we actually need. Because we can write all of this, so how many lines is this? We'll ignore this line, so 1, 2, 3, 4, 5, 6. So this is 6 lines of code. It's actually possible to write all of this in just 3 lines of code. And the way that you can do this is by recognizing that we're dealing with an if. So ifs always are followed by Boolean expressions. What else is followed by Boolean expressions? While statements. While statements are followed by Boolean expressions. So what we're doing here is we're saying, look, in the step 3 version of this, we were checking to see whether we could do a swap. Now we're checking to see whether we could do a swap, and we are only doing this while it's possible to do a swap. So this is a much more concise way of getting across this idea of repeating step 3 until there are no swaps. But there's a problem, and I hope that you've caught it. What happens when the reason that we cannot do swaps isn't that the thing to the left is no longer bigger, but that there is nothing to the left? That isn't taken into account here. So we need to add a check. So we need to check not only that the thing to the left is bigger, but also that there is actually something to the left. And we check that by checking that j is bigger than 0. Because as soon as j is equal to 0, it means that our j is right at the front of our list, and therefore there is nothing to the left to check. So this here is a nice, concise way of repeating step 3 until there are no swaps. So just going back to our for loop version, this will work. This will work quite well. So if this makes sense to you, by all means, feel free to use it. But my personal favorite way of implementing this is this implementation here. All right, so that's step 4. Step 5 is nice and simple. We're just going to move k up by 1. So that's k plus equal 1. And then finally, we're going to repeat steps 2 to 5 while k is within the list. Now, there's nothing fancy going on here. We're not trying to check whether or not it's possible to do a particular thing. This is a much simpler repetition of steps than the one that we just talked about with step 4. So either we could do this as a while loop. K is equal to 1, while k is less than the length of the list. Do the repetition, and then each time you've finished steps 2 to 5, just move k up by 1. Now, many while loops can be translated into for loops. This is one of them. So we could just write this as for k in range, starting at 1 and finishing at length of list. Do steps 2 to 5. I prefer this version simply because it's a lot more concise and it communicates nice and easily that we are setting our k at 1 and then stopping at the end of our list. Once again, I just want to emphasize, this is different from selection sort. In selection sort, it was for k in range 0 to length of list minus 1. In insertion sort, it's for k in range 1 to length of list. So make sure you do not confuse selection sort and insertion sort. In insertion sort, we look left. Our k has to start at 1 because we have to be able to look left. All right, those are all the steps. Let's put it all together. So we started with setting up our k. We then set our j to our k. We then looked to the left and we made a swap if the thing to the left was bigger. So this is our, if the thing to the left is bigger than the thing at j, do a swap, move j down by 1. Then we repeated this while it was possible to do swaps. So this here is our look to the left and lumber. This is where the guts of the algorithm is really getting into play. Then we had to move our k up by 1, and we had to keep doing this while our k was within our list. So that was for k in range 1 to the length of our list, do all of these steps. Okay, so these are all of the steps of our algorithm. Now we need to get rid of any duplicates. I can't think of the word. Get rid of anything that is unnecessary, and we need to put it all in order. So the first thing that is obviously unnecessary is this if statement, because it's all nicely contained within our while loop. So let's get rid of that. Now, if we're going to use a for loop, then it's not necessary to have our k equals 1 and our k plus 1 set up. So let's get rid of those. Then our for loop needs to be up the top, because all of this is going to happen inside of our for loop. So let's do that. All right, and then let's smush it all together into a really nice, clean function. And there we go. So you can see we've got our for loop, so that's the bit that means our k will keep repeating until it's outside of the list, and it also sets up our k to be equal to 1 at the very start. We've got setting our j to k, and then this while loop here, oh, we've got some inconsistent indentation. That's all right. This while loop here acts as our look left and lumber. Now, there are multiple different ways that you could have implemented this. So, this for loop, you could have implemented it as a while loop. That would have been perfectly fine, very acceptable. This while loop down here, we talked about lots of different ways we could have implemented this. We could have used a flag. We could have even done this as a for loop. You are not locked in to implementing anything in this function in the way that it has been implemented here. Please do not feel that just because you have seen it implemented one way, that is the only way to implement it. You also could have decomposed this function. So a very common decomposition is to take the insert aspect of the function and make it its own function. So think about how you might decompose this function in a way that makes it either easier for you to implement or easier for somebody else to read. Remember that one reason that we often decompose things is to make it easier to communicate our intent. And that's a really important thing to keep in mind. Now, if we think back to our example, essentially what we were doing was we were printing the state of the list for each iteration of this for loop. So every time we set up our k and we ran this while loop, once we had finished running this while loop, then we would print our list. And that's usually what you would be doing if you were asked to show all steps of applying insertion sort to a list. Applying the insertion sort algorithm to a list. And that's also why we get, so long as you include the original unsorted list, that's why you would end up with as many states as you have elements in the list, because this is all going to happen length of list take 1 times. All right, that is everything to do with insertion sort. I hope that you've enjoyed this video. Again, please, if you come up with a better code than a better chant, then look left and lumber. Put it in the comments. I would love to hear other people's ideas. Also, if you come up with a wildly different implementation of insertion sort, feel free to put it in the comments. Insertion sort is an incredibly important algorithm. It's actually used in real life because it's very good at sorting almost sorted lists. And if you start learning about complexity, you'll see why this is considered quite a powerful algorithm. This has been really fun. If you have any questions, feel free to ask. Other than that, I think we are done here. See you!